So hi, today we will talk about the forward converter. So it is quite common as the flyback converter, and it's an isolated DC-DC converter as well. So let's have a look at the topology at first. So here it is the basic topology, and you see there's also a transformer in between, and actually that transformer is directly connected to the input voltage as in the flyback converter. And what we have here is the inductor, and there's a freewheeling diode. So actually, I think you can see that part is directly a buck converter. So that is why actually you can see it is derived from the buck converter. So there's a diode, so that diode prevents some current to flow in the reverse direction. So we had the same kind of diode in the flyback converter, but the right hand side is a back converter, and we will see it also in the voltage equations, right? So let's another difference from the forward converter. Let me clean that part a little bit. So what you can hear is the dots are the same direction. So whenever you have current flowing in that direction, so you will have some current going under the same direction. So it's like a normal polarized transformer. So let's try to derive the voltage characteristics of that converter, right? So at first, let's try to calculate what happens when the diode, the switch is on. So let's calculate switch is on condition, right? So if you have VD here, right? So again, normally that converter has, the LM and other components. We will derive that shortly. But what you will see is if this is like I1 and if this is VD, and if that switch is on, that diode, because of that current, will be forward biased, and you will have the voltage coming into that direction. So let's try to plot the VL, and we will derive the voltage characteristics. So let me get rid of myself. So let me first plot I'm trying to write the VL, okay, in on condition. When it is VD, okay, that voltage here, that diode will be off actually, and that will be something like that. So this is my L, and this is my VL. Here is VO, and that diode will be on, the other diode will be off. So that voltage here will be V in or VD times N2 over M1, right? So it is normal transformer ratio. Okay, so VL in that case will be equal to, on one side you have VD times N2 divided M1, right? Minus, and the other side you have VO. So you have that kind of voltage waveform for how long? For DTS, and that value is here. So it is VD times N2 over M1 minus VO. Okay, so let's of course you can see here, let me actually, you can draw it as well, of the current. Okay, so let's try to draw the IL, and we will also discuss what happens with discontinuous conduction mode and so on. But first, whenever you apply a positive voltage, you are charging your inductor. That inductor is charging up. When the switch is off, so let's see what happens. So once you close that switch, I will show it with the red arrow here. So now, okay, so you will have, because you know that thing is off, so that one will be 0, so that current, that one will be 0, but that inductor current would like to flow from somewhere, and that is why, you know, we have the D2, so it's like a freewheeling diode. So that is the current, and that one again will be off. So in that one, let me draw the circuit again. So the primary side is now off. We have the freewheeling diode, RL, and we have that inductor current flowing through here. So of course now my voltage is down to whatever, so my inductor current is, in this case, VL. As you can see, it is similar to buck converter, so it is VL is equal to minus VO for some time, and then the same thing again, right? So of course, if it is working at the steady state, so it will be something like that, right? So here it is dTs, and this one is 1 minus d times ts. So it is really like a buck converter. The only difference is, instead of in a normal buck converter we have as the input voltage we have V1 minus, or V in minus VO. Now we have the added turns ratio. So let's derive that calculation. So of course, you know, you can make that areas equal to each other. So VD times N2 over M1 minus VO, okay, times D should be equal to, okay, it is VO, or you can write the actual value and make it equal to 0, VO times, oops, I think it's, that's just a second, let me, oh. Let me put it here. So it is 1 minus d, right? So you can write that one. So Vd times N2 over N1 times d minus VO times d is equal to VO minus VO times d, and they cancel each other. So you can quickly write like VO is equal to input voltage times N2 over N1 times duty cycle, right? So actually it is so it is like a buck converter, okay? So it's like a buck converter. The output voltage is proportional with the duty cycle, okay? So this is coming from the buck part. But however, we have a transformer ratio, so we have option. Again, in a normal buck converter, I mean, buck converter is always a step down converter, right? You use it, you cannot use it to step up. So here you have the duty cycle that is trying to reduce the voltage, but depending on your turns ratio, for example, N2 divided by N1 is 10, so you can actually boost your input voltage by 10 times multiplied by buck part, buck and duty cycle, let's say 0.5. So using a 10 to 1 ratio at a duty cycle of 0.5, you can boost your input voltage by 5 times. Or if you want to reduce your input voltage, then it is easier, because your duty cycle also tries to reduce the voltage, and you can choose a larger number of turns on the primary side, let's say 10 to 1, and that makes like achieving like larger step down ratios possible. So it is really like a buck converter with added turns ratio. Unfortunately, the converter is not that simple, because we don't have an ideal transformer. We have the other components, and that components can create a couple of problems in the forward converter. So let's have a look at what happens. So it's the same converter, but what happens if our inductor, or our transformer, is not ideal, so that it has resistive components and, more importantly, magnetizing inductance LM, which we discussed in the flyback converter. So here, I mean, you have the LM as well. So you can charge your circuit, and you are supplying some power, but during that time that inductor is also being charged up. And once you close that switch, that ILM would like to go somewhere, but that path is now closed, so it is not like the forward flyback converter. In the flyback converter, first you are charging up that LM, then you are sending energy to the secondary side. But however, the polarities of the transformer in the forward converter is different from the flyback converter. So you are sending power when the switch is on. So that one you are sending power, but once the switch is off, that ILM current has nowhere to go, and depending on your switch turn off speed, what you will have is like LM times d ILM over dt. So depending on, on t turn off time, so this voltage can exit, and you can destroy your MOSFET or any other switch. So we need to get rid of that current somehow, and maybe the easiest solution, so we are looking for a discharging path for that LM. So the easiest solution would be to install a snubber circuit. In the first semester we talk about the snubber circuits, and RCD circuits are one type of snubbers. So here you see this forward converter with added LM. So once you charge it, so that one is being charged, and you are sending power to the secondary. But once that one is off, so now you have, instead of destroying that MOSFET, now that has some path to discharge. So you are basically dissipating the energy. You are storing some part on the capacitor, but some of the thing is being dissipated as heat. So this is RCD snubber circuit. They are also called reset circuit, because it's resetting the magnetizing inductance. So this is a snubber circuit. So by using that kind of snubber, it will be possible to get rid of the excess energy in LM, and you can use non-ideal transformers in that circuit. But the disadvantage is it is inefficient. You are dissipating, again, maybe the energy per cycle may not seem significant, but what if you are running your forward converter at like 100,000 kilohertz, right? So that means you are dissipating that energy that you stored in that inductor 100,000 times each second, and actually it can, depending on your operating currents and the transformer design, actually that can reduce your efficiency quite a lot. So there's an alternative circuit, and actually it is much more commonly used in practical forward converters. Okay. By the way, actually, before moving on, the same circuit here, the problem is the LM, and on top of LM, of course, you can have the L leakage, and we didn't talk about that one. LM is usually larger than L leakage, but in a flyback converter, you can, I mean, yes, you are sending the energy stored in the energy stored in the LM to the secondary side when the switch is off. So that's why you have like reverse polarities here, but there's still the energy in the leakage flux component, leakage inductance component. So you can use the same RCD circuit in the flyback converter. So again, in your term projects, we would like to include those leakage terms. So either you should choose a proper MOSFET that can withstand the ringing voltages of that leakage, or actually you can reduce that amount of voltage on voltage stress on that MOSFET by including some RCD snubber on the leakage on the flyback converter as well. Please have a look at that reading assignment as well. Anyway, so if you move on to a practical forward converter, there is a slight modification here. So in that one, we use not a two winding transformer, but we are using a 3-winding transformer. So that one is extra winding. Okay, so don't get scared. So the idea is like really similar to a normal transformer. So you have, I don't know, you can have the N1 and you can have the N2. I'm not sure if I'm plotting the correct directions, but you can add, it doesn't have to be on top of that one, but the idea is now you are having another thing like with N3. It can be here on top of that one, or all three can be on top of each other. The important part, we will talk about the magnetics design, but the important part is all those currents or fluxes are linked together. So it is not like a separate inductor. All of them are in the same core, and we need to write the Kirchhoff current law or the magnetic equations using these three windings. Okay, so we have just one diode and an extra number of turns in that transformer. So let's see how does it work and what is the purpose of that extra winding. Okay, so it is, here you see like the ideal components, and one is here. So here you see the same thing, okay, but we have the magnetizing inductance like in a practical transformer, and also it's not included here, but you have the leakage component here as well. So that extra path, actually you can see it here, and we will investigate in using mathematical terms, but let's have a look at how it works at first. So whenever it is on, yes, whenever the switch is on, you are sending power, you are charging up that inductor, right? It is the same. And whenever it is off, actually that current cannot flow, and that one cannot flow as well. So you have the freewheeling path. But whenever that one is off, and actually you want that inductor current to flow somewhere else, actually it is flowing through that one, okay, and while it is flowing through that one, actually you have a turns ratio, and that one is, you know, creating some path through here. So using M1 on N2 terms, you can send the energy. I mean, I will show it in other graphs as well, but whenever the switch is off, you are sending that energy back to the source. So instead of dissipating the energy every time and every switching instant on a RCD snubber on a resistor, what you are doing, you are using that extra winding to store, to induce some current on the third winding and send it back to the source. Okay, so the operation of the main forward converter is same. That one is not affected, and we still have the same voltage characteristics. The only difference is now I have a path for LM to discharge. So let's, you know, redraw that circuit, and again, you know, they are the polarity of that one and that one same. That one, actually, you know, that one is drawn here, so it is upside down, so don't get confused. So the polarities are reversed, so we will see that one. So let's investigate step by step how does the current is moving. So let's have a look at a point where the switch is on. So here we have the switch on. Okay, so I have the switch on here. So now my source voltage is charging LM, but also I am sending some current here. Okay, depending on your turns ratio, this is your I1, and you have your secondary current coming out of the main output winding of the transformer, and now that one is on, but that one is reverse bias, so that one is off. So here, like, we have the other diode, and that one is, you know, charging my VLX. So LX is charging, and again, let me write it for the sake of completeness. VLX is equal to, on one side we have Vs times N2 divided by M1 voltage, and minus VO on the other side, and ILX is increasing linearly. I mean, if you remember the previous slides, so it is the same characteristics as we have here, right? And actually, if you look at that circuit, or let me try to describe it in here. So if that switch is on, so if you have some current here, I1 current is in that direction, so I2 is coming out from the direction of the dot, and the same thing would like to happen through here, but now D3 is blocking, so actually the third winding is not carrying any current when the switch is on, so that is why, you know, that one is off, so I3 is 0. So during the on period, it is as if the third winding is not there at all. So let's have a look at what happens with the ILM. So during that time, okay, VLM is equal Vs, and ILM is also charging up, and that is, you know, that is still the case if you don't install the third winding, and if you don't find any path for that current to go, if you turn off that path, it will create a large induced voltage, and you can destroy your switch, right? So that is why we installed like the freewheeling diodes in the buck converter and so on in the first semester. So let's have a look at what happens. Okay, I charged that one. Now I turn off my switch. Okay, I turn off my switch, and now that current, okay, whenever that current is 0, okay, that one is 0, so you would like to actually that normal operation, it is similar. I will tell the effect of the third winding, but that will be 0 as well during off period, and that will be on, and that will be carrying the ILX current. So this was the usual operation. So let's see what happens from the perspective of the ILM. So that current is now charged up. It was increasing when the switch is on. It would like to flow that way, but now that one is closed, so it tries to flows in that direction. Okay, the ILM tries to flows in that direction. So again, if you carry, okay, if you carry some current in that reverse direction here, so that would like to have current here, so that is why D1 is blocked. In the normal case, D1 is blocked because I2 was 0, but this one is now it is blocked because it would like to draw negative current, right? But that polarity again, we are coming into the dot, and that will induce some current through that path, right? So now that current again, it seems like you shouldn't think like it's a normal circuit. They are magnetically coupled, so you can think that one like now you have I1 on one side and I3 on the other side, so you are getting current, and that current is coming basically out of the other direction, and let's see where it goes. So it will flow through here, okay, and that will come back through here. So you are sending your power, okay, sending your power back to the source. So the energy that is being stored, okay, the energy that is being stored in LM is sent back to the grid. So let me maybe it's better if I just drove here. So it is coming from here, and that current is induced on the other one. I will write the mathematical terms, don't worry, but try to understand the basic concept, and that one is now again being discharged. So LM is discharged to the source, and I1, okay, this was, remember, I1 getting into that one. So I1 is equal to now minus ILM. Okay, so I need to write the Kirchhoff current law, or you can think from the magnetics, like N1 I1 is equal to N2 I2 minus N3 I3, because of the polarities of all these three. MMF, you can just write the MMF terms, not the Kirchhoff current law. But anyway, so basically I2 is 0, so I can find the relation. Again, don't think like it's a normal inductor, so you cannot say the current is same current here. They have mutual inductance, and the ratios between the currents is equal to M1 I1 is equal to minus N3 I3. Okay, and we will also discuss that one. Now you want to demagnetize LM completely, and you have time until the next turn on period. Okay, so you have time until the next turn on period. So let's try to write again the equations during on and off times. So again, for the sake of completeness, let's start for the switch is on first. Okay, it's off first, but let me write the switch is on condition. So V1 is equal Vs during that time. Okay, V1 is equal Vs, and V2, okay, it is the secondary voltage here. It is V1 or V1 times N2 over N1 that is Vs times N2 over N1, and V3, okay, you can write the V3 here, so you can write V3 as the same thing, V1 times this time N3 over N1, and that one is equal Vs times N3 over N1. Okay, and you can write the mathematically, if you would like to find the voltage along that one, you can have one voltage here, another voltage there, which is the other voltage. So you can write VD3 diode 3 voltage is equal minus Vs minus V3. Okay, and again it is larger than 0, so you can see it is less than 0, so D3 is off during the first time. Okay, so again I'm not going to derive like all the voltage characteristics, but what you can write is also, you can write the VLM. Okay, the during on period VLM is Vs. Okay, it is equal to Vs for D times Ts, and again we will see if it were starting, but the change in LM current during that period is depending on the time that one is off, so you can write Vs times D Ts divided by LM. So that is the amount of charge that you need to get rid of during the off time. Okay, and again if you would like to calculate like how much current is flowing through that one, you can quickly write the switch current. Okay, switch current is equal to I1 current plus ILM current, and maximum current that this switch need to be carry can be calculated by depending on the load and the voltage and LM characteristics. Okay, so now let's write what happens for the switch is off, right? During switch, I know ILM is equal minus I1, right? During that period, so that one is now off. So this is I1, the first winding, and this is the ILM, so it is its own path. So I can write that relation, right? So I can also write what is V3. Okay, so I can write V3 voltage on the third winding is equal, they are like reverse connected. Let me maybe open here. If that one is flowing, then V3 is minus input voltage. So I can write V3 is equal minus Vs, right? So now let's try to write the V1. Okay, V1 during that time is V3 times N1 over N3, because I can write, again, if you are confused with that configuration, you can write that relation, right? So, and I can write that one is equal to minus Vs times N1 over N3. Okay, and you can write V2, okay, as well. It is V3 times, you don't have to define everything from V3. I'm just following the steps in your book, but you can also define it with respect to the first winding or the second winding. It doesn't make any difference. So that one is equal to Vs times N2 over N3, right? Similarly, you can write the same relations using the MMF in a core, again assuming like a perfect core and there's no MMF, so there's infinitely permeable core. You can write N1 I1. It is similar to like normal transformer, like we have that one, but we have the other polarity N3 times I3, and in the off period I2, I think it's out of the boundary, I2 is equal 0. So what you end up is N1 I1 is equal minus N3 I3, or you can write I3 is equal minus N1 over N3 I1. So you have the same relation, but of course the voltage ratios are reversed. So that is that one. So I can write the equations. Let me go back. Okay, so let's try to calculate how the current in that inductor LM changes. Right, using all the equations are derived, I can also say like VLM is equal V1, okay, here, and that one is minus Vs times N1 over N3. Okay, I'm just using that one to that one, and that voltage, okay, is equal to Lm L DILM over dt. Or I can see the discharge rate of the inductance is minus Vs over Lm times N1 over N3. Right, and the actual again I will come back to that equation, but let's have a look at how that all adds up. So during on time, and this is off time. Okay, so during on time, my inductor ILX is that one, is charging up, and I already know that one, and the off period it is discharging, and the inductance, okay, it is starting from here, and then it needs to come back to the same point. I want to discharge it completely, so I need to calculate how quick that is going to discharge. Okay, I can calculate the maximum current period, and by using that term I can also calculate how much time it's going to take to discharge. And you can ask, why does it have to discharge before the next cycle? So again, I'm skipping a couple of slides, but what happens, okay, if you have either larger duty cycle or you have more currents? We will come back to that figure. But if you have some kind of not discharging completely, okay, for that one, so you will end up at a slightly higher ILM. I mean, even if it doesn't destroy your switch, that will create a higher flux density. And in the next step, so you are adding up on top of that one, so you end up even higher flux, so you end up higher current. So, and that current, remember, at the end of day, so this is your winding, and whenever the magnetizing current draws, you will have some flux core, and that will keep increasing, and that will affect your B core to increase. Okay, so then you will saturate the core. First, the losses, the core losses is going to increase. Then you will have, as the core saturates, its permeability is going to come down, and you will have reduced LM, reduced magnetizing current. So you will have problem in power transfer, so your transformer is not going to operate properly. So that's why we will talk about those things in the magnetics design, but that is why I want to make sure the ILM current is completely zero after the next cycle, so I can operate it nicely. Okay, so if I can calculate, okay, so if I can calculate the rate of change of that one, and I also know the maximum value, I can calculate what should be the relation between these two. So let me write that one. If it is starting from 0 value, then the maximum current here, the maximum current here, like ILM max, will be equal to that value, Vs times dTs divided by Lm, and that delta Tx period should be smaller than 1 minus dTs. And let's calculate that period, okay. So I know it is coming by that rate, so if I divide that rate by that current, I can calculate the time that is required. So I can write that current as, that one, Vs dTs divided by Lm divided by the rate of change of that one. Again, this is reducing, so that's going to be a minus, but I'm not going to write the minus term. Vs divided by Lm times N1 over N3, so that one cancels, so dTs times N3 over N1. Okay, so delta Tx is equal dTs times N3 over N1, and that should be okay. So you can calculate, so the total off period is again that one. Let me draw here, that is of 1 minus dTs, and that should be smaller than 1 minus dTs, right? So you can actually find a relation, you can get rid of the Ts, so you can get that equation here. So you can write Ts can be cancelled, so d times, okay, let me write a little bit forward, d times one plus N3 over N1 should be smaller than 1. So that is our condition. And again, there are some different applications, like how to most optimum ratio for N3 and N1, but the most common one is just use the same, while you are winding that one, just use the same cable, so the cable can carry the same current, and actually you can use the same turns ratio. So it is common practice. Again, there are other applications, but usually these two turns are chosen as same. Let me say common practice. So then that means D, okay, if they are same, okay, you can cancel all M1 over N3 terms. So actually here I3 is the identical, and the reverse direction I3 is equal to minus I1, so this discharging rate is the same as the charging rate. So if that one is cancelled, it is minus Vs over Lm, so while it's charging it is Vs over Lm. So if you use the same voltage ratio, you can write 2D is less than 1, or short D is smaller than 0.5. So it is, if you choose M1 and N3 to be same, in order to demagnetize your core completely, your duty cycle has to be smaller than 0.5. And again, this is a common practice, and you need to make sure, because sometimes your input voltage is changing and you want to again obtain a constant output voltage, so you can play with your duty cycle during operation, but you need to think about your input voltage variation, and you need to choose, because at the end of day, where was it? At the end of day, you have, you know, that ratio in your control. And for practical forward converter, if your duty cycle is going to be less than 0.5 for all operating conditions in order not to saturate your core, so you can choose a proper N2 with some safety factor to ensure your duty cycle is always less than 0.5. Okay. So again, if you just look at the other characteristics, I mean, let's go through those ones. And again, please do the derivations yourself, and all detailed calculations are in your books, either in Hertz or in the Mohan. So what happens here, let me go back to that one. Okay, so let's have a look at what happens to I1. So at first, while you are charging up, so it's going up. Okay, so that is how it is going up. And then suddenly, so this is our on period, and while you come back to off, okay, so the direction of the I1 is suddenly reversed, right? So it is, you are going from positive current to negative current at that instant. That is the ILM max, right? So then it just discharges. So this is your discharging point, and this is all your off period. So before you fire the next, you know, on period, your primary transformer coil already reaches to 0. And let's have a look at for I2. So for I2, whenever that one is on, you are carrying some current, and that current is proportional with I1. But whenever the switch is off, that diode is reverse biased, so I2 drops to 0. So you have the I2 is increasing with the same relation depending on the turns ratio, you know, N1 over N2. Then it is off for all that cycle, and during that all off period, actually the load is supplied by only the LX inductor, right? Let's have a look at I3. So in I3, whenever you are operating normally, when the switch is on, that diode is reverse biased, so I3 is off. So it is only doing its job in order to discharge LM, right? So it is 0 at first, then it just goes up. Then again, you know, that value depends on the number of turns ratio of N1 and N3, but the usual practice is to choose them same. If they are same, then you can say this is ILM max, right? And again, this is our output voltage is coming here. That one, not the real output voltage, sorry, the transformer output voltage. So whenever it is on, you have N2 over N1 times source voltage, and whenever it is off, because of that diode is off and the freewheeling diode is conducting, so you have 0 volts, right? So it is like that circuit. Okay. Okay, so that is, you know, all again, you know, it seems quite strange and maybe difficult at first, but the idea of the, you know, third winding is just to increase efficiency by sending some power to the source instead of dissipating it, but the rest of operation is same with an ideal forward converter. Anyway, so we talk about that one. I think the maximum DS, if, let me write here again, or do I have, if N3 is equal N1, then D should be less than 0.5, and this is the usual common practice. And we already talked about like what happens. This is again the case where duty cycle is less than 0.5, so you have enough time to discharge the LM, and this is what happens if the duty cycle is larger than 0.5. Okay, so let's talk about the advantages over the flyback converter. So you have better utilization of the transformer. I mean, that is important in a flyback converter. Remember, you are turning on the switch, you are storing that energy in the core, in the transformer at first, then you are using that stored energy to send it back to the output, right? However, in the forward converter, the energy is being transferred whenever there is some current in the primary winding. So from that perspective, you utilize the transformer better, because you are, instead of storing it in the transformer first, you can send it directly over to the load. Okay, and because of that, again, we will discuss it in the next week. Usually on forward converters, a gapless transformer can be used, and you don't need a energy storing element. You need a transformer as close to as an ideal transformer as possible. So usually use a gapless core, and that will cause a higher LM, and higher LM means you will have less ripple. And again, if you manage to increase, remember, if you manage to increase LM, so you will have less problem with the maximum current in the LM. If the LM is smaller, then you will have to deal with a larger current here. So transformer design, magnetic design is really important for those isolated converters. And again, similar, like apart from, let me open the flyback converter. In the flyback converter, that one is turning on and off, and whenever it is off, you have just the capacitor to supply the output resistance, and you need to choose a large capacitor, because that current coming in from that side is discontinued, it is on and off. However, in a normal forward converter, it is like a flyback converter, it's like a buck converter. So the current on that one, remember, it is like that. So you have more or less continuous current coming in here. So that means you can reduce the size of that capacitor. Or again, you can think like a square wave on that side. This is an LC circuit, LC low pass circuit, and it is much more efficient to filter out high frequency components than using a pure C as in the flyback converter. So these are, the main advantages over the flyback converter. And the drawbacks are, maybe you have increased cost. I mean, you use an extra winding and extra diode, but in some cases you can even, if it's designed properly, because of the reduction of the size of the transformer core, the cost can be less, but it all depends on the application and voltage characteristics. And again, we are not going to get into detail in the discontinuous conduction mode, but the gain is changing quite a lot, so you need to do a closed loop controller. And if you are using a closed loop controller IC, then you don't have to worry about that one, but you need to be careful if it is an open loop system, and so you need to make sure if it is working in the DCM mode, or when it is working in the DCM mode, what happens to the output voltage. Another thing is maybe a higher voltage requirement for MOSFET, and that comes from the fact that, actually I try to I think show it here, the voltage. Okay, the voltage again, whenever it is on or off, you have those turns ratios, and that will put some stress on the voltage. And actually I would like you to simulate those things in your project assignments, in software project assignments. Okay, so there are also a couple of alternatives. So this is the conventional forward converter, and what you can do is you can also use a 2-switch forward converter, and again, that part is same. Instead of using a third winding, what you can do is you can add, like this is the normal switch that we have, and we added an extra switch and also these diodes. So let's see how it works. We are not getting into like mathematical derivation, but whenever the switch are on, so you are carrying, like you are supplying power, so this is on operation, so this is like normal forward converter. But whenever it is off, you are disconnecting that one, off, and you have the LM. Okay, you have the LM here, the same, but now that LM, because of these two diodes, and that one is totally disconnected, actually that LM now can be sent back to the source. So again, this one, from the efficiency wise, it is really similar to the one with the third winding. You are not dissipating that energy, instead you are sending that energy again back to the grid, but not with a third winding. I mean, here you don't need the extra winding, but you just added these two voltages. So then the important part is like, what is the voltage drop on those diodes? Because if your input voltage is quite small, again, this may not be the most optimum solution because of the forward voltage drops in those diodes. But if your input voltage is high, then that may be much simpler to implement a third winding, and extra, you are using an extra diode anyways in the other one, so you can just add a couple of components and you can have a efficient operation. So that is a good alternative, and again, you can think it in your hardware projects. Okay, so that one again, two switch forward converter. It doesn't require a snubber circuit, less voltage stress on MOSFETs, and you can supply multiple isolated outputs. So the thing is, with the forward converter, actually, let me remove me. So you can have maybe different, I mean, this is a trick that can be used in forward converters. So this is RL, so let's say this is M1, so this is N2, let's say A, let's call that one N2B. So by using different turns ratios on the same core, so actually you can supply different, let me say V out 1, so this can be V out 2, whatever. So you can supply multiple isolated outputs by using the same core with different windings. Okay, and it has the two switch has like low power losses and noise. And another thing is, once you have the third winding, you can create some electromagnetic forces on transformer windings, and if they are not fixed properly, if you are just loose connections, and depending on the operating frequency, if it is in the audible range, if you are switching like at 15 kHz, your transformers can make a lot of noise. And actually, since you have less number of windings in the two switch combination, you will have less acoustic problems. Okay, so again, that's all. The cost depends on the application, but using an extra MOSFET and drives for that MOSFET and extra diode can increase your cost, and you have larger component counts. Another option is to use like interleaved forward converter, and again, we talk about that interleaving in the previous topologies as well. So the idea is, you can connect, like, instead of designing a, I don't know, 2 kilowatt load, and instead of designing 2 kilowatt transformers, that kind of things, you can have 1 kilowatt power transfer from each interleaved converters. And what you can do is, you can introduce some kind of phase difference between these two. So it has a couple of advantages. One of them is, let's say you are operating at 50 duty cycle 0.5, and you just make it shifted. So that means whenever that thing is supplying current, that one is off, and whenever that one is off, that one will be supplying current. so you will have a really low ripple current, and in an ideal case actually you can have some kind of DC current. So that means you can reduce the size of these two components, quite significantly, or with the same inductance and capacitance values, you will have much less ripple. And secondly, not always your supply is capable of absorbing power from your LM. Of course, you can put maybe some extra capacitors, but that extra power flow from the third winding can increase the voltage of the primary side, or maybe you need to choose a larger capacitor. Again, whenever you have some phase difference between these two cores, whenever that third winding is supplying power, the other one maybe is drawing that power, and whenever that one is supplying, it is going that one. So instead of sending all power back to the grid in every switching instant, you are storing energy at first on that core, then you are sending that energy to the other core, and that energy is being transferred between these two cores without going back to the source. So again, interleaving is in general quite advantageous, and you have the modularity, and you can have maybe backup in those interleaved positions, but you need to think about the added number of devices, and again, size wise, it may be larger to implement two 1 kilowatt devices compared to a single unit. Again, it all depends on your application. Okay, so there are a couple of reading materials, so please have a look at those ones, and I think it will be really helpful in your hardware project designs. Okay, thank you.